why don't we get started? Hopefully we'll get some more folks joining us as we go. Right. So first off, just a quick note for those who are joining us from YouTube or a WebEx browser. We're going to be showing a short video from Chancellor Blank after remarks from our CIO, Lois Brooks, and that'll be before the keynote address, so shortly around like probably 9:25-ish. If you are joining us from YouTube or WebEx browser, you may not be able to see the video, just a weird little WebEx thing that we have discovered. But you can find the Chancellor's video on the main website right on the front page if you go to itproconf.wisc.edu. So as we're playing the video, we're going to let people know we're playing it. You can go watch it, and then you can come back to the stream. Um, so welcome and good morning to the 2020 IT Professionals Conference. We are super excited to have you all here today. And I've got to say, it's a beautiful morning, and it is amazing that we are all here together. So we're excited to have everybody, all of our attendees, all of our panelists, all of our moderators. But we are going to start off on a little bit of a somber note. It is with a heavy heart and that we open this conference, as we know that there is a lot of unrest and pain being felt in our community and across the country right now. We felt that we could not start this conference without acknowledging the current situation. This slide has been intentionally filled with the beautiful artwork that's on and around State Street as a result of boarded up windows and shop fronts. We show this art in solidarity with our colleagues of color. We as a community agree that Black Lives Matter. In that vein, I'd like to ask that we take a moment of silence to remember those whose lives have been lost due to police brutality. Let's remember the names of George Floyd of Minneapolis, of Breonna Taylor of Louisville, and remember the names of those closer to home. From Milwaukee, Dontre Hamilton, Ernest Lacey, and Silva Smith, and remember Tony Robinson from our own Madison community. Thank you. Now, we want this conference to be a welcoming and inclusive space for all, which brings me to our code of conduct, which we show every time. I'm just going to read it. The UW IT Professionals Conference is dedicated to providing an inclusive and engaging conference experience for everyone. We expect all conference attendees and speakers to be professional, considerate, and respectful to all with whom you come into contact at our conference, including fellow attendees, speakers, and event staff. We value you, your safety, and your participation, and we appreciate your help in making this conference the very best that it can be. So what does that mean in a virtual conference? What that means for us and for everybody is that we ask that you be kind. In this online conference, it means listening to the moderators, being considerate of others in discussion, and giving everyone a chance to talk who wants it, and leaving positive comments and questions. It's really, really difficult when you're in a virtual conference to remember that the person on the other side of the computer is still a person. And so we want to make sure that everybody is leaving feedback and positive comments to those people. Any negative comments about a presenter or community member is not acceptable and is grounds for being asked to leave the conference. So please be kind to one another, be considerate, please listen to the moderators. And as we go, the conference is a lot of back-to-back sessions. So because we don't really need to worry about the space and somebody else coming in, maybe times where the session runs a little long, and that's okay, but being sure that you're listening to the moderators when they tell you the session is over. So we want to give a huge thanks to all of the folks that are listed here. The Office of the CIO, IT Connects, Jason Persane, Gina Gomez, Laura Bellman, and all of the presenters and moderators and the IT community at large. And I want to give a special shout out to Sarah Lean, who is moderating this right now. So thank you so much for that. And then also Al Nemec, sorry, I don't know how to pronounce your last name, that is doing the live stream on YouTube. We couldn't have done this conference without all of you, and it is really great to have this much support on campus. So let's talk a little bit about what is going to be going on today and tomorrow. Oh, sorry, I don't have my thing. First off, also our conference committee. So my name is Mandy Morrow. I am one of the co-chairs, and my other co-chair, Elizabeth Simcock, is also on here. We had an amazing project manager this year, Mary Cummins, and as you can see, the steering committee, lots of people, and then also all the additional committee members. Again, we could not have done this without everybody here on this list, and even some people who also may be missing from this list. I tried my best to put everybody on here. So let's talk about what's going to happen. All right, so today, June 4th, we are currently in the welcome and keynote, and that will be going until about 10:30-ish, and there'll be a little bit of a break. And then at 11 o'clock, we have the IT Communities of Practice Forum, a live session. At noon, I will be running lunchtime games. You are all welcome to join if you'd like. It's best to have a mobile device with you so you can play the games, but you can also play on your computer. Then at 1 o'clock, we are going to have user-centered collaboration in siloed workspaces. And then at 1:30, telling your IT story to non-IT audiences. At 2 o'clock, we're going to have a live Q&A for one of our pre-recorded sessions, IPv6. So if you're interested in that live Q&A, we recommend watching the video ahead of time. Also at 2:30, we have managing passwords with KeePass. And then at 3 o'clock, our weekly IT Connects community has been incorporated into our conference. So that's going to be going on at 3 o'clock, just a nice networking space, lots of birds of a feather conversations going on. And then at 4 o'clock, we are going to have our closing keynote, which is on cloud computing. So that is our schedule for today. As always with a conference, and especially a virtual conference, that does not mean you have to attend all of the sessions. You're welcome to jump in and out as you will. Go ahead. There's also plenty of pre-recorded sessions, and we'll give a little snapshot of some of those. But you are welcome to do that as well. Tomorrow, our sessions, starting off at 9:15, Lois Brooks is opening up her office hours for everybody to join from 9:15 to 10 o'clock. At 10 o'clock, we have a humble inquiry about learning how to ask questions in the workspace. Then at 11, there's a distributed developers coffee hour. And then at noon, our project manager, Mary, is going to be running lunchtime yoga from noon to 12:30. At 1 o'clock, we have the art of influencing change. At 2 o'clock, we have another live Q&A. This one is Cloud Data Strategy and Interoperability Initiative. It's a joint live Q&A from two different pre-recorded sessions. Also at 2 o'clock, we also have another live Q&A for multi-user Samba mounts on Linux. And then at 3 o'clock, we are going to be having our first ever IT awards brought to you by the IT professionals. So be a great session to learn about what's going on around campus and your colleagues who are doing exemplary work. And then lastly, at 4 o'clock, we are finishing our conference with a virtual happy hour. And we hope all of you can join us. It'll be a lot of fun, a lot of conversation, maybe some breakout rooms. It'll just be a space to chat and join in to celebrate the end of hopefully successful conference. So we also have plenty of pre-recorded sessions, like I mentioned, and I have a little snapshot here. I did not put all of them on here, but here are some really great on-demand sessions that we wanted to highlight. Some that are more focused for particular users, and some that are a lot more general. We've got Building Wisconsin Public Radio's Next Gen Radio Operations Center. We also have a session on Making Meetings Matter. Another one on meeting DoIT's computing needs. Another session on Introduction to Terraform. Another session, Desirability, Usability, and Accessibility, Creating Your Best Website or Service. Got Transition to the Public Cloud. Another one, this one had the live Q&A, IPv6 at the Hygiene Lab. And then another one, Data Under the Hot Lights of Google Data Studio. So these are just a few of the many on-demand videos that are out there, and we encourage you, if you have a live session you don't want to see, to go ahead and jump in and watch some on-demand stuff, or also these will be available on the website for at least the next week or so, and we'll let folks know when we decide that we're taking them down. So you have time, if your schedule seems really, really booked today and tomorrow, there's also going to be time to watch these after the fact. All right, so we want to make sure that everybody has the opportunity to join, to network, to connect, and especially in this virtual conference, we want to make sure that there's a space to chat about stuff, to ask questions. So we have a conference Slack. It is the same one that it was last year, if you or in years past, if you have been to the conference before. It is uwitproconf.slack.com. You can go there, and there are plenty of channels connected to this year's session. Each session has its own Slack channel for the most part, so you can check in on there. There's also a general. This particular session is 2020-Keynote. So how do you find a channel in case for some reason you're not seeing it? Just walk through really quickly. On the uwitproconf.slack.com, you go on the left-hand side, there is a channel dropdown, and there's a little plus sign next to the channels. Mine's in black, yours might be in white, but there's a little plus sign, you hit the plus, and it's going to bring you to a little menu, and you can go to Browse Channels, and you can then search for the channel you're looking for. So as you can see, the 2020 Keynote is one of the ones on there. I took this screenshot before anybody else joined things. But there are plenty of them in there. Also, all of the sessions under the website, if you go to the actual page with the description on them, near the bottom, there is a direct link to the channel. So if you want to just jump in that way rather than trying to search for it, that works as well. There is one channel in particular that I'll talk about that in a second. Apologies, I don't have a next slide, so I'm trying to remember in order how these things work. So as we always like to do at the conference, we like to talk about how life is better with data. And so I want to go over some really great data points for this year's conference. First and foremost, as of this morning, we had 314 people registered for the IT 2020 Professionals Conference, which is a huge deal for us because we've only had 30 we have 31 more people registered this year than we've had in the past. Also, it's been approximately 11 weeks since we decided that we were doing a virtual conference, and we transitioned from an in-person conference to a virtual conference in 11 weeks, which sounds like a lot of time sometimes, but it really is not. Also, we have 19 pre-recorded sessions that are happening. All of them are captioned for those who need it as well. So 19 pre-recorded sessions, all captioned. And we have 20 live sessions and events. I did include the virtual lounge in that number to make it different than the pre-recorded sessions, but that's a lot of live sessions and events going on as well. And then, last year we had 247 units of coffee powering our day. Um, and that's some data that we've had for the past about how many units of coffee. And so the question is, what about this year's coffee? So some of you have already found this, but I want to point out that we have a lovely channel called the Coffee Counter, the 2020 Coffee Counter. We want to make sure that our coffee data is kept up to date. So if you go to either the live session or the on-demand, along the right side, there is a button that'll bring you to the Slack channel for the coffee counter. And when you get there, you can add a coffee emoji or tea emoji whenever you get a refill. I will say you can add other emojis as well, but we will periodically be using a little widget in Slack to show how many cups of coffee are going on throughout the day. So anytime you get a cup of coffee, make sure you do that. If you already had a cup of coffee and you haven't marked it yet, please go in and do that because it's just all a fun way for us to keep our data up to date. So again, I just want to thank you all for being here. It is a very exciting day. And on that note, I am going to pass it off to Lois, who has a few words for us.
Thank you. Good morning, everyone. Welcome to IT Professionals. Last year, I was still fairly new and took the day to go to the IT Professionals Conference. And it was just so much fun. I want to, before I get to the prepared remarks, just take a moment and speak from my heart with thanks to the conference committee, to Mandy for beginning this with a human moment, acknowledging what's happening in our communities and in our country. And just say this to my Black and Brown colleagues: you belong here. You are valued and respected. I want to work with you and I want to learn from you. I am committed to creating a workplace that in every interaction values your expertise and welcomes you in every way. You belong here. To the entire IT community, I need to acknowledge this last few months that we've been through. We are operating a university that rests entirely on your shoulders at this point. All business, all operations, all teaching, most of our research is being done virtually, just like this conference is. That was a huge lift for the IT community. And all of you reached in, gave a hand in the lift, and we did it. We pulled it off, and it is working. I could not be more proud to be in your company. For the people that organized the conference, thank you. Thank you for putting this together. For all of you who have developed content, I'll just say first, thank you for taking the time to become an expert in a topic, and then thank you for taking the time to teach, to share your expertise. That's an act of generosity. To our keynote speaker, Mary Poppendieck, thank you for coming here to virtual Wisconsin with us and taking time to teach and share your expertise as well. It matters. And then for all of you, just kudos to you for investing in your own professional development. The, the university is going to continue to rely on your expertise, on your ability, your skills, and your knowledge. And so taking these few days out to learn, to improve your skills, to invest in yourself is also an investment in the university, and I'm grateful to you for that. So with that, I will close off, hand off the microphone back to Mandy and the conference committee, and say, everyone have a great conference.
Thank you so much, Lois, for that and those words. At this point, as I mentioned, for those of you who are still didn't hear at the beginning, we are going to show a video from the Chancellor, and for those who are joining us via WebEx browser or via a or via the YouTube stream, you will probably not be able to see this. So if you cannot see it, that's okay. You can join us in watching it by going to the IT ProConf main website, and it's right on the front page if you scroll down a little bit. So with that, I am going to bring up this video. So those who are, again, joining us through a WebEx desktop should be able to see this. Everybody else, you can join, and we'll give you time to watch it and come back. So it's about a minute and a half video. So here we go. Right. I'm going to give those folks who are watching a moment to come back.
Can't hear anything.
Oh, we're coming back in just a second. We're giving those folks who are watching separately a chance to join us back. Okay, so I want to just, before I give our introduction to our keynote speaker, I want to just have a little note here before we go about how the keynote Q&A session will work. For those of you who are joining us via via Slack, you have the 2020 keynote channel that you can use for that. Well, I guess all of you are joining us from WebEx or YouTube, but you can use Q&A in Slack. Also, you can join in if you're in the WebEx, you can chat at all the panelists, or in YouTube, you can put comments in there for Q&A. And what'll happen is that we, as a committee, are working to curate all of the questions, and we will bring them. And Amanda Thornton will be asking the questions. And she'll be asking them at the end of the session. So if you are in WebEx, please don't raise your hand or use the reactions in WebEx. We will not be following those. So either put your questions in the Slack channel, in the WebEx chat, or in the YouTube comments, and we will ask the questions for you. So it is my pleasure to introduce Mary, who started her career as a process control programmer, moved on to manage the IT department of a manufacturing plant, and then ended up in product development, where she was both a product champion and development manager. Mary has joked that she has considered retiring many times, first and foremost in 1998. Before she found herself in managing a government software project. And that led her to writing her first book, Lean Software Development and Agile Toolkit. And she has gone on to write many other books about implementing lean software development, leading lean software development, the lean mindset. So lots of books and lots of talks that she has given in the past, and we are very excited to have her. So at that point, I am going to pass the ball to Mary once I can exit out of this, the joys of jumping back and forth. So thank you, Mary, for joining us.
Thank you, and good morning. There, now I can share. And I'm trying to find my content to share. Try this. Okay, what do you there? Oh, that's not the right one, but there we go. So is that the right slide? That's the front one? Thank you, and good morning, everybody. My name is Mary Poppendieck, and I've been doing this software stuff for over 5 decades. And so I thought it might be interesting to take a look back to the way things started. And if you go back over 50 years ago, Tom, who's here, and I were university students. First at Marquette, where we met, and then Tom did his senior year at the University of Wisconsin, where he graduated. And then we moved to the Washington, D.C. area, where I got a master's degree at the University of Maryland, and then back to the University of Wisconsin, where Tom got his PhD. So we're very familiar with the university there and love it a lot. But Tom was also a university press photographer. And throughout the time at Marquette, he did pictures for the daily newspaper or weekly newspaper and for the yearbook. And for example, here's a picture of the Selma Sympathy March at Marquette in Milwaukee in 1965. When he moved to Wisconsin, the thing to note is that we actually were an unruly cohort of folks at the colleges in the country at the time. 68 was let's just say, quite a wild year. And here is one of the demonstrations on Bascom Hill, of which there were many. And then when we were in Washington, D.C., massive protests against the war. And here, for example, is 1969, where buses lined the park to keep people, the street to keep people out of certain areas. And as you can see, 500,000 people showed up. It was the largest demonstration in Washington, D.C. to date. At the University of Maryland, after the Kent State incident, we had a sympathy demonstration, closed the streets down for probably too long. And here is where we had let's just say a pretty impressive clearing the campus curfew. The stuff that's happened recently gives me a lot of throwback to these times. The other thing is that we did all of this without social media. Influencers came to campuses. That's where they came. So that the voices of people who wanted to be heard very often would show up at the University of Wisconsin, or at the University of Wisconsin in Milwaukee, or at Marquette, or places like that. And so all of these pictures are pictures of presentations that Tom took. And these are the folks that influenced our generation. But at the time, technology was really primitive. If you take a look at the time when we went to college, every engineer had a slide rule, and we knew how to use them because that was the only way that you could do any kind of calculations. In 1964 was when the first mainframe was announced. And if you take a look at that little chip on the left, that was a very, very tightly packed integrated circuit at the time. It was pretty amazing. And in 1965, the very first electronic switching system for telephones was installed in Schenectady, New York. And that is a picture of it. It's pretty big racks and racks of equipment. In 1969, Apollo landed on the moon. And if you take a look at the bottom, you will see in the center the control panel that the astronauts used and a couple of boxes. And that constituted hand-wired boxes, by the way, and that constituted the entire computer that orchestrated the moon landing. My first job in 1967 was at Bell Telephone Laboratories, where I worked on the number 2 ES electronic switching system, the one that was for community exchanges for the smaller suburban systems. And this is what it looked like. It had, again, something that might be called integrated circuits, a lot of discrete components. But we had a design goal that the cost to install this had to equal the cost to install equivalent electromechanical systems, and it had to be just as reliable. The problem is that electrical mechanical systems were very reliable because one relay died, didn't matter. There were all kinds of other thousands of relays, and they could just find a different route through the system. That meant that our reliability goal was a maximum of 2 hours downtime in 40 years, which is 3 minutes a year, more than 5 nines, and probably the most aggressive downtime goal I've ever seen. So the question is, did we make it? Well, pretty much. I read an article by our project manager some years later in Computer Magazine that said, yep, indeed, the system did not have more than that amount of downtime. But on the other hand, in 1990, a failed rollover at one suburban station started cascading throughout the whole US, and the whole half of the phone system was shut down for 9 hours. There was a fear of a terrorist attack, and all sorts of things didn't happen. You know, we've seen this other times. When a network, it might be an electrical network, an electrical grid, or it might be any kind of network where one little piece fails and cascades throughout the entire network. And it's that cascading that was not quite expected in our overall design. So let's talk about what were the themes in the 1960s in the area of working with computers. The first theme was software engineering. In 1968, there was the software engineering conference because they needed to address, in the NATO conference in Garmisch-Partenkirchen, to address the software crisis. And the software crisis was involved in the fact that software had become more expensive than hardware and was getting increasingly expensive and wasn't actually doing what people expected it to do. So that was when software engineering started to be thought of as a separate profession, a separate concept. In 1968, in Datamation, Conway's law was very first published. You've heard of it. It basically says your system architecture and your organizational architecture are going to basically be the same thing. And that law has continued to be true for all of the decades I've been in the business ever since. And we were trying to do very large systems, like, for example, the telephone system that I worked on. And we knew that reliability meant redundancy. There was no concept that you could have all those discrete components with no failures. We knew discrete components failed. And so we had massive redundancy. Well over half of the software and hardware in our telephone switching system was duplication. And isolation, especially fault isolation and isolation of individual components. And then the ability to control locally what's going on so that you don't depend upon some central coordinated system to make things work. Which led in the 1970s to ARPANET. And I remember when I was at the University of Wisconsin going to an ACM evening meeting. We had ACM meetings every month in the evening. And that's where most of the UW computer folks got together from different areas. And that's when ARPANET was there. And at this talk that we went to, there was somebody from BBN, both Barnick and Newman, talking about this thing called an IMP. That's an interface message processor. And in that particular time, we knew that this internet was not really as reliable as it needed to be. We had those interface message processors that were talking with each other, And if you take a look at this architecture, it looks exactly like the architecture of the telephone system that I had been working on. Those IMPs were the electronic switching systems that were in every neighborhood, and hooked to those were the little were the individual computers, just like we had individual telephones hooked to our telephone switching system. And we know that has the problem of cascading network failures. And so if you go to France at the same time, they became interested in what was going on in the US with ARPANET. And so there was a system called Cyclades by Lois of France. He came to the US and he said, well, we really would like to do something like what you have, but you know, those amps that you have, they look like what a telephone switching system is. And our phone companies, for example, they're not going to be interested in switching data from individual computers or individual sites. There's too many of them. Every country has its own national phone company. So we have a better idea. We think that we should make the host responsible for data exchange. And the folks in the US said, well, good luck with that. And so he went back home and created the Cyclades network, which actually worked, which had no central control, and which made the host responsible for data. A couple of years later, the TCP/IP protocol designed by Vincent Cerf and Robert Kahn used the Cyclades concept as their basic principle, that each distinct network had to stand on its own with no internal changes required, that no information would be retained by gateways and routers, that there would be no global control at the operations level, and communication would have to be on a best efforts basis. Up until TCP/IP, and it didn't really take over the internet until the early 80s, you had to acknowledge every single message that was sent. And as you can imagine, every so often the acknowledgement or the send would get lost and the system would lock up. And the way that we had to get past that was to put all communications on a best efforts basis. So it's 1971, and I arrived at Madison, Wisconsin with a master's degree in math from the University of Maryland, an 18-month-old daughter, a year of programming the #2 ESS computer at Bell Labs, and a husband, Tom here, who was embarking on a 5-year PhD program. So pretty obviously, I needed a job because he was not going to do too much to have to bring in enough money to support us. And so I got a job working for Murray Thompson in the high energy physics department. And what he was doing was digitizing bubble chamber film, massive reels of film taken in 3 dimensions, focusing down on traces through the Fermilab. Well, at first it was the Argonne Lab bubble chamber in Chicago area. And this is me in 1973 with my daughter, now a little bit older, and my son. And down in the physics lab, where we worked on all sorts of interesting projects on a mini computer that was a cast off from a company that went bankrupt. We had a couple of those, and we had a huge amount of electronics that was put together to scan this film. And actually, by the way, went with Murray when he moved out to the Stoughton area to start working on the Singleton Radiation Center. But then in 1976, we moved to Detroit, and I got a job at General Motors as an engineer working on a driverless vehicle program that they had. We were doing wire following and cruise control for vehicles as they slowed down to 0, which was pretty novel at the time. And my programming was in assembly language on a Texas Instruments 990, which only had assembly language. And I was having a lot of trouble getting it to work. And so I decided I needed to go back to first principles and figure out what the algorithm was that I was programming. So I bought this book, which you can see is a little bit beat up. That's because I read the whole thing, taught myself control theory, and discovered that the engineers had given me an algorithm program, which has actually had a gain, which was 2 orders of magnitude out of whack. And so I went with my control theory knowledge and said, maybe there's something wrong with this algorithm. And they said, oh yeah, you're right. So they had assumed that since I was programming in assembly language, it had to be the computer's problem. It wasn't, it was the algorithm. So after a year of that, Tom moved to a job in Minnesota here. And so I got a job as an engineer at 3M. And what I was doing there was designing control systems for this kind of process where we take film and coat it with stuff and cut it up into little pieces and sell it as, when in my case, it was magnetic tape. This is what a process control system looked at like in 1980. It had a mini computer. Mine was HP 1000, but typically it would be a DEC PDP, say 11. There would be an operating system, some recipe storage, some historical records. And then we had a bus that was an interrupt bus. And on the ends of the bus were PID controllers, proportional integral differential controllers, which provided the analog control for the temperatures and the pumps and the heaters and the coolers. And the computer would send them set points, and then it would get some information about what the things were doing. And everything was actually controlled by the PID controllers. And we also had PLCs, programmable logic controllers. These were programmed in ladder logic, the same kind of programming scheme you used to program those telephone system relays that used to be in the telephone offices. And those were programmed by some other engineers. I never actually learned ladder logic, but I interfaced with it a lot. And we would send events back and forth to each other, and then the individual events would be controlled by the PLCs. So you can see that the mini computer wasn't really a trusted member of this family. It would send stuff out to what we today call edge computers, and then hope for the best. Because we knew that anything that can go wrong will eventually go wrong. And when you're controlling processes with explosive potential, you do not assume that the computers are going to work right. You always assume that something will fail. So what we have here is in 1970s, software that was event-driven, driven by interrupts. It was object-orientated. It was orientated around motors and pumps and healers and coolers and timers and switchers. And the predominant mode was edge computing. So in this sense, nothing is so new these days. So the themes in the 70s. One of the themes was the responsible engineer. Engineers were responsible for the design and development of a component, for making sure their component operates properly and does its job as part of the overall system. We didn't have the concept of project management, which had a detailed description of what you do, and then you figure out how to do your part. We had a completely different concept in engineering, which I think is maybe returning. And we focused a lot on fail-safe design because, as I said, we knew that anything that could go wrong eventually would go wrong. And this was a decade of structured programming, starting with Dijkstra, Edgar Dijkstra, who said, if you want more effective programmers, you're going to have to stop wasting their time debugging. You have to stop introducing bugs to start with. So you need methods to do that. If that doesn't sound like some of the things that Agile has tried to teach us in the last 20 years, it's pretty close. There was also top-down programming, and the idea there was what today we call continuous integration. You get the top level working, and then you add a piece, and you add a piece, and you add a piece, and at every step, you make sure that things work. So interesting ideas that finally came back a couple decades later. In the 1980s, I became a technology manager at a 3M manufacturing plant. Here it is in Hutchinson, Minnesota. And we manufactured videotape. At that plant, I implemented I was instrumental in helping to implement, let's put it that way, one of the first just-in-time systems at 3M. My boss said, you're not just in charge of computer systems, you're in charge of any information flow systems that we have in the plant. And we basically threw out my MRP computer system and replaced it with a manual pull system based on Kanban cards. And we figured out how to do it by ourselves because we predated most of the consultants in the area. And so it was kind of interesting that we figured out how to do just in time ourselves. And because we figured it out ourselves, it was very successful. We focused on reliability, on quality, on safety, and upon rapid flow of materials through the plant. And it was rather dramatic when we finally cut over to a pull system just in time. We went from being able to fill about 65% of the orders on a week-to-week basis to about 95% of the orders on a week-to-week basis, because we stopped trying to push stuff onto workstations and started trying to pull from the orders at the beginning of the week. It's really important, I learned, to think about flow as a very important concept, but to give you an idea of how you have to think differently about flow. Flow is not about being efficient. Flow is about all those vegetables on that cart not spoiling, and about getting the vegetables to the market and to the people who are going to eat them while they were still good. And we still do very large amount of perishable goods flow. And in a perishable goods supply chain, you never optimize for resource efficiency. It doesn't make any sense. You don't want to have the most efficient bike out there. You want to have the fastest way you can get those vegetables to market. You never accumulate large batches in a bigger vehicle. What if I had a tractor and pulled it with a trailer? Because the small batches got to market faster, got to the customers faster, got eaten faster, and they were fresher. You aggressively discover and eliminate the biggest bottleneck that's keeping your vegetables from getting to the people who are going to eat it. And then you just keep doing that. And you use the consumption to pull replenishment through a very short, fast supply chain. And by short, I really mean local, and maybe bikes are faster than trucks when you think about local supply. And you leverage the consumer feedback, what they said or did, or what they bought or didn't like, to make product supply decisions. That's what flow is all about. And anytime you think about how your milk and meat get to you, you have an idea about a perishable goods supply chain. It's a little bit fragile, but it's got a different concept than efficiency as the thing that you optimize for. There you optimize for throughput, not for everybody being busy all the time. In the 1980s, there was a big push for user programming because that's when the PC was invented. This is my son, Dustin. You saw him when he was a baby. Now he's 13 years old. And our first computer, that's what they looked like those days. And he learned to type because it turns out that he thought typing was something that was helping him do his schoolwork. So we had word processors. I introduced spreadsheets to our manufacturing plant so we could do our budgeting every year on computers, on mini computers rather than by manual computations. And that was the same decade that fourth generation languages came in, and we got all kinds of great report generators, which were going to make programming unnecessary. So why do we need programmers? If we can have these report generators and users can do their own programming, people can program at home, who needs programmers? Well, we'd asked this question before. COBOL was going to do the same thing. It was going to eliminate the need for programmers, and that didn't work. And it didn't work here because the higher the level of the language, the higher the level of complexity that you can put into a system. And you always reach a point of complexity where you really need to think much harder about it than the casual user is interested in doing. And I think you've probably seen this cycle yourself. So people who really pay attention to how the technology works and how much complexity it can handle are always going to be needed. So in the 80s, the themes that we saw, execution matters. You have to have expertise. You have to have focus. You have to pay attention to detail. If you want reliable systems that scale, that are usable, that are safe, that are secure, it's not something that happens because you hope it happens. It happens because you pay attention to detail. You pay attention to experts. You focus on what matters and make sure that things happen. in a manufacturing plant or any execution environment, any operational environment, attention to execution is really important. The other thing is, that's when I first understood that flow was really important. Flow all the way through the beginning to the end of a system. You don't suboptimize at a particular point and figure if you optimize every individual piece, the whole thing is going to be optimized. Because if you did that in a flow system, you could optimize for the biggest trucks that you could have. You could optimize for the fastest way to get your produce from here to there, but you still are not optimizing for field to table. And so you need to focus on the whole system. And the other thing you have to do is not manage tasks, not manage individual either tasks for manufacturing equipment or individual tasks in a project, but for the whole flow of projects through the task. Oops. And there's the last one, and that is Parkinson's law. Parkinson's law for software basically says the complexity is going to expand to fit the latest abstraction available. And so don't worry, there's always going to be complex systems to deal with. In the 90s, I became a product development manager at 3M. And here I am, the second row, the first, second, third from the left. And I assembled a light fiber team. And this happened because 3M was in the film business. And as film became replaced by digital, it, like many other disrupted companies, was not able to replace its digital systems, its film systems. Like I was working on aperture card systems for engineering drawings. We tried to put multifunction printers on that could print CAD stuff, but we never seriously got into replacing our aperture card systems with digital systems. So I went and worked on plastics, fiber. This is a team that did a light fiber with a very bright end light. And we developed some innovative manufacturing processes, and we commercialized this product in the US and especially in Japan, where they sold it very typically to the automotive industry and other Japanese industries. Unfortunately, when this picture was taken, most of my Japanese team was not in the building, so we missed out on them. But this is a large amount of the rest of the team. It wasn't a really big team, but we did a lot of really interesting things. Now, in the 1990s, I was not in software, but in software, because in the 1980s, things got kind of out of hand with user programming. What came in the 1990s was seriously heavy focus on process. And that's because of the disasters of the 80s. So in that time frame, it turns out there was a big time frame between releases, starting to work on a release, and when it actually got released. You know, it could take six months. It actually usually took a year or more, and 18 months was short for many releases, to start working on something and then get it out to production. Typically, code freeze was 30% or more of that cycle, sometimes up to 50%. And in addition to that, before you started working on any release, you had to completely decide everything that was going to be in the release before you started working on it. So typically, you froze your features half a year to 2 years before they actually got released to production. This was a cause of massive amounts of very slow software releases. At the same time, while this was happening in big companies all over, especially IT departments of big companies all over the globe, something else was going on. There was this, first, I guess you would call it a blog today, and then later a book by Eric Raymond called The Cathedral and the Bazaar. And he talked about what he thought was the way to do architecture. It had to be pre-planned. It took a while, but boy, you got great results in the end. And then there was the bazaar, where you had all these tiny little shops with their own owners doing whatever they wanted. Well, there was some organization like the vegetables were in one place and the time was set by the organizers. Basically, these were independent shop owners. And much to his surprise, he didn't think that a bazaar could ever work for software engineering, but the cathedral and the bazaar said, you know what, you would be surprised at how well the bazaar works. So if you look at what's going on at the same time as we have those big processes, in 1991, a Helsinki student started up writing an operating system just for fun, okay? And in 1993, 8 developers started looking at the web server that was developed at Champaign-Urbana and figuring out how to make it something that would work for them. In 1999, Linux had a $1 billion investment from IBM. And by 1999, the Apache Software Foundation was used, their software was used by more than 40% of all websites, was founded, excuse me. And today it's used by more than 40% of all websites worldwide. That's a pretty amazing decade when we found out that this concept of a bazaar actually works better than the cathedral. And to many of us who had spent the early years working on sort of small things and mini computers, we weren't that surprised, but a whole bunch of people were. So the themes of the 1990s. First of all, there was the cathedral. There was big standard processes, plan the work and work the plan. And then there was a bazaar. There was the free and open source software. And they were really in very strong opposition to each other because the bazaar didn't really have a process or plan. It had local responsibility. And guess what? It ended up with better software. Wow, who would have thought? At the same time, 1990s, especially as you got to the middle of them, was so focused on Y2K, which everybody was terrified of, that especially in big companies, many of the cycles of people's thinking and focus that would have gone to other things went to Y2K readiness instead, because they figured the world was going to fall apart when the date hit 2000. It didn't. You know, I was programming software back there when I was programming computers back there when we didn't worry about whether or not the date had 2 digits or 4 digits. And the reason is because those mini computers that I worked on, they didn't have batteries. And so when you turned it on, you had a state. It was the state that had no date, no time, no concept of anything, and everything that you put in was put in by you. You maybe didn't even have BIOS in the early mini computers. And it's because of that, we didn't use dates. In a control system, you don't need dates. All you need is elapsed time. And we never got elapsed time from dates because they couldn't be trusted. And so I knew for a fact that most of the really old control software never conceived of the concept of data as being a critical element. But, you know, I wasn't worried. My daughter was. Now let's take a look at the year 2000. And I'm going to call the year 2000 the decade of teams. In 2000 itself, that year, Kent Beck published Extreme Programming Explained, and it was about embracing change. Because up until that time, at least in the decade before, everything was focused on change is bad. If you're not working according to a plan and executing it, you are like less than professional. And there was a focus on working software. So in 2001, the Agile Manifesto was published and says, guess what? We got a better way of doing things. We want to focus on some other things than process. And so that's when the Agile Manifesto came out. And what you saw then was the Agile movement taking over and changing the way companies thought about what it meant to build software. But, and I'm not going to say a lot about Agile, I'm just going to pretend that you might know about it. But the question I always have about the Agile time from 2000 to 2010 is, were we building the right things? Because we were not worrying about planning anymore. We were doing things very extemporaneously. maybe a little too extemporaneously, because our focus was on optimizing for one thing, maybe not optimizing for the whole system. So we were optimizing on something different, not on process, but on rapid response, but we weren't necessarily optimizing for the whole system. So it comes time to, let's take a look at the themes in the year 2000. One of the themes was the year 2000s was when multidiscipline teams became a thing. Up until that time, if you were in software, you had your own office and you had your own thing and you got your tasks from somebody else and you did them and handed back up to a pool. But we started to have teams that could do many things. The problem with that was there was, of course, the benefit of that, excuse me, was that when you had a lot of different disciplines, if you put somebody from each discipline on a team, you had a much easier time coordinating across disciplines. That's the hard part. The easy part is coordinating within a discipline. The hard part is coordinating across disciplines. The other thing that became a big thing there was incremental delivery. Large projects, long release cycles, those were the things that made you professional in the 90s. They kind of fell out of favor to smaller things and faster release cycles. And the third thing was that there were product proxies. In the various Agile movements, there was people called customer representative or maybe product owner or the business. People who told the software team what they were supposed to do. They were proxies for customers. And you might guess that I was rather surprised at that concept and didn't quite understand it. And to this day, I think it was the biggest mistake that the Agile movement had. And then we come to the 2010s, our last decade here. And that was a decade of flow. These two books, Continuous Delivery, was published in 2010 and DevOps Handbook a couple of years later. And it had everything to do with rapid delivery into production. When you think about the year-ish release cycles of the 1990s, and then you think about continuous delivery anyway, at least every day, and then every hour of delivery of this decade, the difference is phenomenal. But it turns out that the bazaar style and flow, when you put the two things together, you tie your teams very tightly to the results of what they do, and the feedback cycle is much higher. So you finally close the loop with customers that you need to do in a perishable goods supply chain. The biggest bottleneck we found in the last 10 years were dependencies. Because going in even to 2010, this is what enterprise architectures tended to look like. There was the business and there was a great big centralized database, a single system of record, and that was important. You didn't want to have multiple systems of record because you might have multiple information, different information about things. But the problem was that centralized integrated database was a massive dependency generator. If you changed anything in a single system and it changed anything in the database, all of the rest of the systems might be affected and you had to figure it out. And this was really the cause behind their long release cycles. At the same time, especially if you look at the history of what happened at Amazon a decade earlier, the concept of microservices became a much bigger concept. At Amazon, it was you build it, you own it. You have a small team, they do a small service, they own it, they figure it out, they figure out who their customer is. So you take that architecture on the left and you build something a little bit more like the architecture on the right, where you have a cloud and a technology platform sitting on top and a bunch of services with applications. And the services have their own distributed data stores. And if you told me in 2005 or 6 that Amazon didn't believe in a central database, I would have told you that they were crazy. You had to have a central database, or else maybe they knew something I didn't know. Turns out they did. So the concept of how do you deal with eventual consistency, how do you deal with distributed data stores and still get you what you want is what we learned in the last decade. But with all these independent services and all these independent teams, we came upon another problem. And that is, how do you coordinate all these tiny little teams so that they can accomplish a single mission? And then we move back. I want to ask how SpaceX does that, because it's a really interesting way to think about how you coordinate a bunch of little independent, capable teams. So if you take a look at the way that they think about how they're going to figure out how to do engineering, they have what's called a philosophy of responsibility. And that is that each engineer is responsible for doing their own piece, for understanding the big picture and understanding how their piece fits into that big picture. So you have a triple responsibility. I get my piece, I make it work and make sure it's done right. I look at my upstream suppliers, my downstream customers, and I understand where I fit into the big picture, and I make sure that it all works. So John Mattoni, who's the SpaceX launch director, and they did an amazing launch yet again this last week, said that no engineering process in existence can replace the philosophy of responsibility for getting things done right and getting things done efficiently. And I think we finally came back to that philosophy of responsibility that we had when I was back at the University of Wisconsin, is we knew no better than to look at the whole picture and have everybody responsible to understand the whole picture. As things got bigger, we tried to divide it into pieces. And now we're sort of back to where we were, where we have the whole system is what we have to think about. So the themes of the 2000s and 10s: focus on flow, don't suboptimize, manage getting the throughputs through, not the tests. That's one of the things that came through from the past. The second theme, here's Conway's law. It hasn't gone away. If your system architecture and your organizational architecture don't match, well, guess what? They will match. So either you need to change your organizational architecture or your systems architecture if they're in dissonance, because one or the other is going to win out. And then there's the concept of the responsible engineer. Engineers are responsible for the design and development of a component. They figure out how to do that. They have to make their component operate successfully and properly, and it does its job as part of the overall system. So that's what we ended up the decade with. Now what's next? Well, you know, we had this big black swan event, maybe two of them now. And these have all happened in just the last few months. And I think the theme for the 2020s is we have to know how to deal with and prepare for black swan events. So this is a bridge, was taken out. This is in Iceland. And Iceland sits on glaciers and volcanoes. And every so often, and they don't know what's going to happen, there will be a volcano under a glacier. In the center of this, the island, it's a glacier in the center and people living on the edges. And there's this one spot where there's Circle Road, which goes all the way around, and you can even see some houses under the bridge there. It spans a big river valley. And every so often, the glaciers blow off, and then the water eventually gets, first of all, pools, and it gets trapped. And then it comes rushing down this river valley and takes out everything that's there, including the bridges. And so after they took out their first bridge, or maybe their second bridge over the river, they built an even bigger bridge, and it took that one out too. I mean, there was another, it lasted a few years, and then it got wiped out. And they finally said to themselves, you know what? We got to stop fighting this. When something happens, we need to be prepared to deal with it. So instead of building a bigger bridge, they built a good sized bridge, and then they stockpiled so that when the next, the glacier and the volcano took out that bridge, they would be prepared to build the next one really fast. And if you think about black swan events, the thing we need to think about is resilience. The thing we need to think about is ways to adapt really rapidly. The thing we're going to have to learn how to do, and what you learned how to do in the past few months, is very rapid response to whatever happens. So in conclusion, I want to talk about sort of the theme from the beginning. What changes? Technology changes. My goodness, there's been a lot of technology change in the last 20, 50 years. The marketplace changes. It will always change. Whatever was best practice 15 years ago, 5 years ago, is not going to be best practice next month. I assure you. Standard processes, interesting, but they change all the time. And if they're not changing, they should be. System architectures change all the time. But what doesn't change? Well, organizational structures change too, by the way. But what doesn't change are, what's really important are the outcomes of the systems. We have to figure out how to think of the whole system and not suboptimize any individual piece. Most of our problems come from optimizing for the wrong thing. Great engineering doesn't change. In fact, the new scarcity these days is not money or anything like that. It's the bright, creative people needed to keep the world moving, especially in our world, in our technology area. And ownership. I gave a talk in 2009 with a guy that was big guy in the open source movement. And what we were talking about was the comparison of the Agile themes to the open source themes. And, he concluded his talk with a very interesting comment. He said, we might not do all the things you Agile folks do. We might not do all the testing. We might not do all the working software stuff. But there is one thing we always do. And he put up a slide and it said, we care. And because we care, things work. And it's that we own it, we care, it's our software. We are going to make sure that it works. That is behind a large number of the successes of stuff that you would never guess should be successful. So here's the basic charter that you work with to enable innovation and scholarship through high quality, sustainable technologies and services. That's the system, that's the systematic thing, that's the overall system thing you're looking for. And you do not want to suboptimize on any individual piece of it. So with that, I'd like to say thank you, and I'm ready to take some questions.
Uh-oh, I think we might have lost the audio for Amanda. I can see you moving, but try again. She looked like she was about to ask a question.
Did I unshare?
If you want to, go ahead.
Okay, there we go.
Amanda, you're still muted.
Am I back?
Yes.
I hear somebody. Yeah.
Okay.
There we go. Okay.
Hi, Mary. This is Amanda. I will be. My friends here are funneling questions to me, so I have some questions that are gathered from Slack and WebEx and the YouTube stream.
Cool.
First off, I want to say thank you for the lesson on sort of the themes across time for architecture, for systems architecture, for organizational architecture is completely fascinating. My career spans like 2000 forward, so I've seen a lot of those in. I certainly saw it through the 90s.
Relatively recent set of years.
I'm also from Kent, Ohio, so it's really cool to see that.
Oh, yes.
And we do have a couple of compliments in the chat on Tom's photography, so thank you, Tom.
Okay.
Now the inevitable question, when you put the bomb in the presentation, can you explain why product proxies and product owners are the biggest mistake of the Agile movement?
Oh, okay. What they do is they take responsibility away from the technical team. I never worked with an intermediary between me and the people I was writing software for in the plant or wherever. I didn't have a project manager. Well, I did actually when I was doing some of the process control work. There was a project manager. We got a basic schedule and we knew, when things had to happen, but absolutely no detail. The engineering manager told us as engineers in 3M that when you put automation into a manufacturing plant, the worst thing you have to remember is that the operators will make product. And if your system gets in their way, they will defeat your system. Okay? And if they defeat your system, it's your fault. My fault as a software engineer, not a product manager's fault, not a business fault, not a customer representative fault, my personal fault for not understanding what that operator is looking for. When I couldn't get my software to work at General Motors, I studied control engineering because my software wasn't working. I had to understand the algorithm I was programming. I couldn't go to the intermediary to say, it's your problem. So when we put an intermediary between a technical team and what they're trying to accomplish, we take the ownership away from the software engineers. And to be frank, I never, ever worked in an environment where there was an intermediary between me and figuring out what to do and setting priorities and dealing with tests. Now, that doesn't mean, if you take a look at SpaceX, it doesn't mean there isn't a mission. There aren't deadlines and stuff like that. But if you look at the teams of SpaceX, they don't have somebody telling them what to do. They have somebody that says, your rocket fuel has to get the booster from here to here, or your landing legs have to make sure that it lands on this shaky ship in the ocean. And it's your job to figure out, what does it take to make that happen? And there's a deadline, okay? And that deadline is the next launch date. And that deadline ain't gonna change. Much as you would like, launch dates don't change. So every team knows what it has to do. They know when the test is gonna be to see if it actually works. And they know they had better figure out all of the surrounding stuff to make it happen. When you take and put that in responsibility to do that figuring out on somebody else rather than the technical team that's actually doing the work, you take away from them the ownership of the responsibility for their product.
Now,
that is in the last 20 years.
Now, if you're, so I think as a software developer, this is a follow-up to that. As a software developer, sometimes we're writing software for very broad, well, I'm writing web software that's going to be on a website, and my user base is the entire world. You know, how do I, or it's the student population.
Okay, so what's your feedback mechanism to know if it's good?
I don't deal with audiences that large, but I will defer to that answer to somebody that's listening.
That's what continuous delivery gives you the opportunity to do.
So I think analytics is as close as we can get.
So I don't know, the real question is, when you're working on something, do you understand the overall system goal of why you're doing your piece? And do you have very rapid feedback as to whether or not you're moving in the direction of that system goal based on what you did in the last month or last few weeks?
Sure.
If not, maybe you should say, how do I get to that point? Because that's what our technology allows us to do today. It allows us to say, and that's why I believe that continuous delivery followed on the heels of having an intermediary. Because what continuous delivery does is allow you to take the actual customers of the end customers of the system and understand how your piece is affecting and impacting the overall system results as opposed to an intermediate system result. And too often we've been focusing on, and it's much easier when you have a proxy to focus on what that person says rather than whether or not it does the job in the field. So just think about it. When I was an engineer, I was told if the operator doesn't like your system, you personally, you engineer, you are at fault because you didn't understand the operator. You have to figure out what it means to write a system that the operator will find convenient to use. And if you can't figure it out, get out to the plant and talk to them. And that's what we were told. And that's what we did. And I was in a meeting with some people. They were government employees. And there was somebody there who had been around since the, I don't know, maybe 80s or something like that. And she said, and it's maybe 2012 or something like that. And she said, you know, I think this Agile stuff has been good in shortening release cycles and stuff like that. But there is one thing that it has taken away from us. We used to be responsible for figuring out what to do. and now we aren't anymore. Somebody is telling us. I just think that's wrong. I think we need to have the engineers understand why they're doing it and care about it in a way that they can care about it. And we have now the technology tools of very rapid feedback to allow that to happen. So if you have to stop at an intermediary spot, you know, in a company, people say, oh, the business is my customer. That's nonsense, okay? They're not your customer. They're not the ones that are, sometimes they used to be when what you were doing was automating their processes, but that was what happened in the 80s, right? Especially in the middle 1990s, as we started having internet software products rather than software process automation, our customers were real people that were using our stuff. And if you don't have feedback from those people as to way you think about how you do your technical job, you will have a different mental model about what's good than they did. In fact, I know a really very senior engineer that I really respected at IBM who said, it's been shown again and again that support calls are bear a direct relationship on whether or not the programmers or the software engineer's mental model matches the user's mental model. If their mental models don't match, you're going to have support calls. So it's getting those mental models together. And when you have an intermediary, it's way much more difficult.
Then you have a translated model. So
from analytics.
Okay, I have a little bit longer question with more explanation if it doesn't quite make sense the first time through. So
okay,
a question from Andrew is move fast and don't break things where this is going, and better dependency management, resilience engineering, and frequent shipping with virtuous feedback cycles.
Well, we never did move fast and break things. Think about SpaceX though, okay? When they launch, they have a date. And it's lucky that they basically weren't developing their landing boosters under government funding, because have you ever seen the video of all of the explosions of those boosters as they tried to land them? There's a wonderful video, and they exploded again and again and again and again. It's because they didn't wait till they were positive it was going to land. They waited until they were ready to test that everything was working. And for about 4 years, pretty much it crashed every time. But if you were behind the engineer behind whatever went wrong, you could expect that within 24 hours, Musk would expect a complete description of what failed and a complete explanation of how that was never going to happen again. So it's not wrong to break things. It is also not wrong to have poor execution. So when I was in manufacturing, execution really mattered. And we didn't break things. That wasn't the concept. We needed to have high quality and resilience. So when we did our just-in-time system, we found that the flow actually increased quality, not decreased quality. So I think there's this fast and sloppy is a mental model from another era. Fast and very disciplined is the right model, but it doesn't mean disciplined is not about going slow. Discipline is about having feedback and being instrumented to make use of that feedback and to constantly learn and get better. And I'm not going to buy the move fast and break things. I'm not going to buy the never break anything. Things are going to break, you'd better be prepared. That's going to happen because the first things we programmed had discrete components, and you already could look up tables about how often every component on the average, the mean time to failure and mean time to repair. So all of our work at the Bell Labs was based on known models of mean time to failure and mean time to repair. So we know things break, but we have to be able to make sure that when they break, they're contained, that the failure doesn't propagate, that the failure doesn't do damage, and that the system is resilient enough that it can recover rapidly. And that's where all the discipline comes in. Not it should never break. It's gonna, okay? Thinking that you can make something that'll never break is like a sort of a errand that you're never gonna succeed in. But thinking about how to deal with it when it breaks, that's something that we spent a lot of time doing, because I worked, as I said, in a manufacturing plant where most of the areas were explosive areas. If you had the slightest spark in the area, the whole plant could explode because of the fumes in it. It's sort of like a grain elevator and our manufacturing process. And so we built walls that would blow out if there was an explosion. Every single lab at 3M had a blowout wall. And maybe in my time there, which was 20 some years, we had 2 explosions on our research campus in Minnesota. And nobody got hurt. Because every lab there, you know, it doesn't, not just those 2, but every lab had a blowout wall. Because one of these days, one of these labs is going to blow. So you plan for failure, but you don't introduce it. And you have people that are responsible to make sure that that's not supposed to happen, but should it happen, first of all, it doesn't do damage. Secondly, you recover fast. And thirdly, you learn so that it'll never happen again. So that's my take on move fast.
Thank you. I'm going to leave.
Move fast and break things is kind of simplistic. The goal is learning. And as academic people, you understand learning through experiment. Now, if you are doing experiments and you get it right every time, you have failed, because failure is learning new things. Any competent researcher knows very well that something on the order of 50% disproved hypothesis will give you the maximum rate of learning. Now, to complement that, you need to worry about these blowout walls. Purpose of these is to limit the blast radius. Do your learning with small experiments so that if you are wrong, as you should be frequently, it won't do much damage. So it's a totally different thing than just breaking things. It's a matter of learning things.
Sure. Thank you. I want to remind people it's 10:30. We want to respectfully your time. Mary, can you stick around and answer a few more questions?
Yeah, the timing is up to you. We're fine.
Okay. Yeah, our next event is at 11, but I want to make sure that if people need a break, they can take one.
I'm happy to stick around.
Great. We've got some great questions in here in this thing that I'm going to go through. Sorry, I'm taking a breath. So I have a little bit longer question here. So Conway's law shows us that as the university is organized equals how the IT will be organized. We strain against that, and this conference is one of those strainings to make the IT community cohesive. How might we incentivize all of us to view further up the value chain and further down the value chain, or even better than incentivize, what else might we do to institutionalize that mindset instead of it happening by happenstance and on relationships only?
Which mindset? Which mindset do you want to institutionalize? I didn't quite understand that.
Okay. Phil?
I understand that you have lots of, I mean, I was part of this. I worked in the physics department and had very little contact with other people doing software, except, as I said, we had our monthly evening ACM meetings. And I'm trying to understand the concept you're trying to institutionalize. I know now that you have various types of professionals that are in computer technology, have some organization that supports them, but no, tell me what the question is. I understand that much.
I can't see Phil's follow-up. So seeing the whole chain and then seeing how they're connected. So you said we need to see the whole process as we're working on our software, and how do we incentivize that view or taking that view, and then how do we get that view?
Okay, I'm going to guess it makes sense to have a sort of communities of practice as a computer technology environment where, for example, when I was there, ARPANET was new, and it was how can we use ARPANET in all of our research. So there's advantages there. But to me, it's the whole picture has to do with me sitting in high energy physics. What am I trying to accomplish? And how can I use my skills to make sure that when we are scanning this film, we get the fast, responsive research work so that they can further whatever research it is that they're trying to do. So to me, the question, the big picture was more about high energy physics research and understanding what they were trying to accomplish and figuring out that how I could help. Then it was worrying about learning about all the different software technology that was available. But as a software professional, my skills, I had an obligation to learn as much as I could about what was available so that I could help my university organization become more successful. And I'm not sure how you institutionalize, I'm not sure what you're trying to institutionalize, but if you sit in any area of the university, what's its mission? What is it trying to do? And how can you bring your background and technology skills to help the mission of that organization be accomplished? And I know that in the last few months, as you rapidly reconfigured the university to remote learning, everybody really understood what the mission was, right? You had to get the technology working. You had to get the laptops working. You had to have students get online at home. I heard all of that in the introductory talk. There is nobody that didn't understand what you were trying to do. And everything, all your decisions were, here's the mission, here's what we're trying to do. We've got to get everybody up online so that they can continue learning, even though they're home. And we have to do it as expeditiously as possible. And we've got to get over whatever, barriers there are in the way and rules that might have been here for other reasons so that we can make this happen. And yet we still have to respect the fact that we've got possibility of, virus attacks, people trying to get into our university computers. We have to make sure we're still secure and still safe, but we have to get online. And you had massive demands on your time, and you didn't have to spend a lot of time asking anybody, what should I do? You kind of knew what the mission was, and you focused on it, and you made it happen. And it's that environment that I think we need to have in lots of the stuff that we're doing. If you're not feeling that in your day-to-day work, you might ask, why not? Why don't you know what your current mission is so that you can make those decisions? You see what I mean?
Yes. All right, I have a follow-up that might be a very tiny microcosm of what you're saying. Janet asked, as a follow-up to your remark about support calls rising when the engineer's model doesn't match the user's model.
Yeah.
Should tech support people who are answering the phones be included in the process? Or I guess maybe the technologists be answering the phone?
I was working on a project at the state of Minnesota, where we were trying to automate the websites that did UCC, which was analyzing this Universal Commercial Code and the corporation's registration process. And we were going from an old system to a really modern system. And we got to a point where we had a legal deadline. We had to have something online, and we weren't quite ready. So we started having weekly meetings we would deploy on Monday, and then we would have weekly meetings. And those weekly meetings were led by the tech support manager, because all we were doing every single week was responding to the calls that came into the tech center so that we could make stuff easier for the people that they were. We could not have possibly proceeded without having not just somebody from tech service on the team, but the whole strategy for the next week was developed under the leadership of the tech support manager, because we were deploying too soon, stuff that wasn't ready, stuff that didn't quite work, and who was suffering was the support desk, of course, right? And so, and it worked really well to have the tech support manager lead the meetings, because then we always hit the really important stuff. So I couldn't be more in favor of making sure that tech support has a great big voice in what's going on.
I suspect the DevOps movement was a result of that communication needing to be put back in place. You know, it got separated somewhere, and then it needed to come put
a
back.
long time before for efficiency reasons.
Yeah.
And by the 1990s, people were spinning off their support systems to, you know, call centers in another country. And
Sure.
like, what good did that do? So there was like the feedback loop was forever. That's why we had these massive long release cycles, because there was no concept of rapid feedback cycle.
A local company has just done that in Madison very recently. So the mistakes continue.
Right.
I want to thank you for mentioning communities of practice. There's a community practice forum at 11 o'clock. So that was, we enjoyed the shout out there. Thank you.
Yes, when you can get together, even though you don't work with people, but people who have your same technology and same problems, you can learn so fast and you can share interesting things to do and stuff like that. So I would say, like, if you take a look at other specialties on campus, and there are some, in our physics lab, we had people that were building the equipment that was doing all the film scanning, not just people who were programming it. And they never actually had a community of practice of technicians doing electronics work, maybe until the physics, the PSL, I think it was called, that Murray headed up, got established. And that whole lab then was a sort of a community of practice of people building equipment for experiments. So we were a little bit luckier because we had the ACM group, and ACM was the big thing at that time. And we had really interesting talks once a month, so we could get together with the, I don't know, 30 or 40 other people that were doing software on campus.
That sure sounds like a community practice to me. All right, we're going to shift gears just a little bit. Scott asked, you've talked a lot about change. Do you have any impression about the speed and amount of change kind of over time?
Oh, you would be amazed. It doesn't change.
So it's not accelerating. It feels like it's accelerating.
Every decade that I have been in, I wrote my first Hello World program in 1961. Okay. And every single decade that I've been here, the remark at the end was, wow, things move fast in the last 10 years. Wow, things move fast in the last 10 years. Wow, things move fast in the last 10 years. I mean, it just kept going on, because if you think about Moore's Law, you know, with the hardware curve going up that way, in 1950s, hardware was way more expensive than software, and nobody even thought about software. But every single decade, there's been massive changes. The one thing that you do not want to do is get into this field if you don't like change, because it's going to happen. And I love the concept of something new every single decade. But if you got to sort of stabilize and stay in, you know, 2015 for your career, you need a different career.
That's for sure. If you're not uncomfortable, we're not comfortable.
I've just never not seen this be an area for rapid change.
All right, I got a question from Julie. If I heard you correctly, excessive dependency was a hallmark of the 2000s. As a technologist of 40 years, hi Julie, I feel like hidden and excessive dependencies have always been a big problem. Can you?
Okay, yes, you're right. I am with you. But I remember in the 1990s when I worked at 3M, there was this huge effort to get everything into a single corporate database, because it turns out that, you know, we have this customer and different divisions are dealing with the customer and they might be telling them different things. And so we have to have one single database that tells us everything about every customer and everything about every product. So in the 90s, there are definitely hidden dependencies is kind of like the long-term and forever problem. But in the 90s, there was a push to invent dependencies by creating massive corporate databases. And at that time, it was considered almost imperative that companies had one single database that held all of the important corporate data, one system of record. Wrong, but there was a whole 10 years when even I believe that.
Speaking of the Y2K problem, I worked in a very large corporate environment, and it was all COBOL programs. So they had millions of lines of code with only 2 digits of year, because it saved space, the hardware. It saved the hardware cost, and then they had to take several years to find every single place there was a 2-digit code, because
they were controlling the infrastructure. That would not have been true. So we worried about, water plants and stuff like that going down. So when in those years, I did not work in corporate areas where there was such a thing as a date. I worked on equipment control. And I was quite sure that people that were programming mini computers to control water plants and, infrastructure stuff in that time would have been crazy to use a date as part of their theory of how they were going to control something, because computers did not have date implicit in them when they went down. You had to type in the date every time you turned the thing on. If you wanted a date, you had to type it in. If you wanted a time, you had to type it in. Remember those days? The person who asked the question probably remembers.
Oh, Julie, maybe.
Since you had to type it in, and you could certainly get it wrong, and it was a pain, and it probably wouldn't happen all the time. So you couldn't make your control programs deal with date. Now, if you had a corporate computer that had operators that were responsible for bringing it up when it went down, and you could put on their list of things, be sure to put in the date, then you could count on date. But we were working with raw computers that if they went down, the plant engineer who knew nothing about computers was going to turn on a switch and reboot it. So then we had to be able to figure out how to bring our computers up from nothing with no human input, and certainly therefore no date. So I was pretty sure. My daughter says, "Haven't you loaded up your basement with water?" And I said, first of all, it's not going to be a problem. And second of all, I've got a great big water heater downstairs. It has water. What the heck? and she had plenty of water in her basement just in case. And I said, this is not going to be a big deal. I'm sorry.
Well, the company I was working for was very concerned because they used the COBOL to generate credit card statements, and they didn't really want to charge people interest from 1900.
That was probably an important concept for them.
All right,
I don't. A lot of COBOL programs kind of disappeared,
and it's still there. I lost my questions. Let's see. I don't think we have any more questions that I've seen on what's posted here. So thank you for your time, and thank you for giving us a little bit extra time there at the end. It was a great conversation.
Yes, thank you very much, everybody. Great. It's nice to see some people that I'm talking to.
And Communities of Practice Forum is at 11, so take a break and join. I'll be in there too. So
great.
Thank you.
Thanks a lot. Thanks, everybody.
Thank you.
Okay, now I got to figure out how to get out of here. How about stop sharing? There's an X here. Shall I push it?
Yes.
Bye.
Bye. Thank you, Mary.
Leave event. Leave event.